In this lesson, we're going to be looking at J.J. Thomson's experiment. Now, the first thing that I definitely want you to make sure you annotate in your notes is that J.J. Thomson's experiment fundamentally was an experiment to determine the charge to mass ratio of the electron. So please make sure you get that in there. Sometimes they will have multiple choice question just asking you what was J.J. Thomson's experiment doing. Well, what it was doing was measuring the charge to mass ratio of the electron using a cathode ray tube. So cathode ray tube technology was the fundamental technology behind the old big tube televisions, and we can talk more about that in class after we understand what the basic technology was doing. And what Thomson did in 1897, which was astonishing considering the state of technology in 1897, was still dirt roads, and really electricity was just coming into its own in terms of having light bulbs and houses and cities getting electricity throughout. So what do we have here? Well, the first thing we have, and one of the most important things for you to learn relative to problem solving in general, is this crossed fields technique for the electric field and magnetic field. So please, again, make sure that you get into your notes that when we're talking about crossed fields, over here, crossed fields, that we are talking about the electric field and magnetic field exactly at 90 degrees to each other, E perpendicular to B. So in physics, if you're told that you're working with crossed electric and magnetic fields, not just that they cross each other, but they are crossing exactly at 90 degrees. Okay, let's see what we have. Well, the basic apparatus actually is going to utilize 3 voltage sources, and I'm going to start out by describing the voltage source over here, the one that is used to heat up a filament, like a filament in a light bulb. It gets hot, it gets white hot, and in this case, we're interested in the electrons that are generated off of the atoms in that filament. So basically what that filament is used for is a source of electrons, and you can think of it as just puffing an electron cloud around the filament, so this cloud of electrons around the filament. And then we have a second voltage source down here that is used to pull those electrons to the right. So that whole cloud now is getting pulled to the right. So you have this big, thick cloud going to the right where it is going to hit a collimating plate, which is nothing more than a metal plate with a pinhole in it. And the pinhole in the middle allows the electrons to go through, and that's our beam of electrons. This big puffy cloud being accelerated, remember, negatives get attracted to positive, so the polarity of the plate is positive. We touch it to this voltage source, and we get our stream of electrons. Now, we have a capacitor here in purple in the middle. I'll talk about that in a second. But for right now, the electrons at the beginning of the experiment travel down undisturbed and hit the 0 point on this phosphor screen. It glows, and that's my 0 point, which we're going to call our 0 point. When I say it flows down undisturbed, it flows down undisturbed because it is flowing in a tube that has been evacuated. So it's evacuated with a vacuum pump to pull out air. So to pump out air. I want to sneak that in there. It pumps out the air so that the electrons go through undisturbed. They don't hit air molecules and get absorbed or deflected by anything else in the way. All right, so what we have then is the situation where we have our 0 point, and now we are going to put our third battery on, which is the battery that is going to go across the purple capacitor that I have shown here, and it's going to generate this downward electric field. So we have an electric field going down, pulling the electrons up when we put that voltage on. Well, we can vary the voltage to vary the strength of the electric field, and we can take those electrons and pull them up and let them hit a spot above. So, and that's what Thomson did. So he had his max voltage that he used, gave a max deflection point up here, and we have our 0 point here. Okay, now to understand the mathematics of what was going on here, we need to take a look at what's going on between the capacitor plates. So the L here, if you're using colors, make sure you have that L color the same as this L. So this purple plate on the bottom is the purple plate on the bottom here. So that distance L is the length of the plate that the electron travels through. The max deflection point is the point here in this diagram. The 0 point is the point down here. And now we're going to look at the mathematics and physics of what's happening to the electron as it travels through the plates to that max deflection point. Well, as it's going through the plates, and there is a B here, but we have the B field is off, so we can generate that B field simply by putting a large north pole of the magnet out of the page and a south pole of a large magnet into the page, and then the B field goes from north to south into the paper, as shown there with those X's that the B field is looking at into the paper. But for right now, the B field is off, the E field is on, and what we are looking at is what is going on between the plates as the electron travels the distance L through those purple plates. So we have this L distance, and this is the force that the electron is going to feel, and it is pulled upward because electrons travel backwards against electric fields. We have F equals QE equals MA, and look, voila, we get into our equations, or Thomson got very quickly into his equation, the charge to mass ratio that he was looking for to determine for the electron and get his Nobel Prize. And if you can see, even from this first equation, he was almost there, because that's what he wants, the charge to mass ratio. The electric field is known. He already knows that because he made it, right? He has the voltage between the plates equals electric field times the distance between the plates. The distance between the plates would be known because he could measure that. So the electric field is known. If he can determine the acceleration, then he's in business. Well, that's the hard part. That was maybe easier said than done. The mathematics is very easy because F equals Q equals MA. It's a constant acceleration. And he certainly could use geometry, since he knew the max deflection point, to get the delta y. Acceleration, right, we said, is what he wants. But here's the hard part. You would need to be able to measure the time for the electron to travel through that distance L. So the time to travel through that distance L was not easy. Those electrons are moving very fast through a very small distance, so speed equals distance over time. L over V equals L over T. So if we again backtrack here a little bit, L we know. So L was known. If he wants T, so if he knows the speed that they're traveling with, he can get T, plug it back in here, and then he has his Nobel Prize because A is known. And this is where the crossed fields comes into play. What Thomson knew was that when he puts on the B field, and the B field value would be known because, again, he's generating it. And when we talk about electromagnets, we'll talk about how it would be possible for him to know the exact value. But for right now, let's assume that B would be a known value because he's making it. B is into the paper. Now, if we do QV cross B, all right, let's do QV cross B. B is into the paper. So let me go back here and get a color. So B is into the paper, all right? So that's B. QV is to the right, so it's streaming down. And if we do QV cross B, that would be thumb up, but we reverse it to get the magnetic force down. So we have the electric field pulling up. QE is deflecting up. Remember, that's our max deflection. Now the magnetic field is pulling down. And when they equal each other, you get no deflection. And if you can see what's going on here, Thomson got excited because he could now measure V. QV cross B, crossed fields, 90 degrees, equals QE. Q cancels. So V is now known because it equals E divided by B when he increases the B field to the point where you get no deflection. So no deflection. And there you have it. Voila. V is known. Once V is known, T is known because L is already known. Once T is known, delta Y was a measurable value. A was known. Once A was known, he had his charge to mass ratio. He went and collected his Nobel Prize. So, fascinating experiment. I hope you learned a little bit and could understand what it was that Thomson did and how he did it. And we will talk more about crossed fields in class, so you'll get more practice with that, both in homework problems and from discussion in class. And we will move on to another interesting discussion on magnetic confinement and magnetic bottles. So there you have it.